Alright, welcome to the fourth seminar of our series. So I'm glad to introduce you Professor Hüseyin Arda Ülkü from Gebze Technical University. So Dr. Ülkü received PS, MS and PhD degrees from Gebze Technical University. It was not Gebze Technical University.
It was Gebze Institute of Technology.
Alright. So in 2006, 8 and 11 respectively. So between 2007 and 2011, he was research and teaching assistant in the same department.
It is 2016.
16, alright. So he's now...
I hold the position.
Alright. So he's now an assistant professor at the same place. So he was also a postdoctoral fellow with the Division of Computer, Electrical and Mathematical Sciences and Engineering at KAUST. And his research interests include the field of computational electromagnetics with the focus on time domain integral equations. And today he will present quantum-corrected plasmonic field analysis using time domain sensitive equation solvers. So I leave the stage.
Thank you very much for the introduction, and I'm thankful to you also including this event. Today I'm going to talk about characterization of transient electromagnetic field interactions with nanoparticles, structures, plasmonic structures, using time domain surface integral equation and quantum corrected model. I want to introduce myself again. I am an assistant professor in Gebze Technical University with the Department of Electronics Engineering. And we started this work when I was a postdoc in King Abdullah University of Science and Technology. And we worked together with Ismail Mesuysa, who was a PhD student there. Now he's a postdoctoral research scientist in Weekend. And Hakan Bağcı, who is an associate professor in KAUST. So my talk has two parts. First, I want to talk about computational electromagnetics a little bit. I want to give some information. Then I will move on to the actual topic, quantum corrected model. Okay. So in computational electromagnetics, we want to estimate or model field propagation, field scattering, or the effects of electromagnetic fields we solve in real life. And how we do that, we use Maxwell equations and we solve these equations and characterize the field interactions. But these equations are very interesting. First of all, they are accurately represent the fields, electric and magnetic fields. And it's another important property is actually if you want to analyze a nano antenna, you use these equations. Also, if you want to analyze the channel between the outer galactic space, then you use these equations. So these equations are great for different length scales. Similarly, also if you want to analyze the static case, you still need to use these equations, and till terahertz frequencies, these equations are great. So it is valid for different frequency scales. And at last, there is another property. These equations are also relativistic invariant. So if you are in a different inertial frame or Galilei reference system, then these equations remain the same. So it is very interesting equations, and James Clerk Maxwell's contribution is actually adding this one to the equations. Okay. So we have some auxiliary equations to complete the system. We have two relations, Ohm's law, where the material properties involved, and we have the equation of continuity. This slide I took it from Professor Chu's seminar in 2015 in Illinois, University of Illinois. You can find this slide in this presentation in YouTube. But I think it shows the importance of the electromagnetics because it has lots of application areas, like from computer chip design to remote sensing, non-destructive evaluation, EMC, EMI analysis, antennas of course, radar problems, we have microwave engineering. If you want to characterize channels, and even it doesn't matter if it is wireless, with wiring, microwave engineering. So it is everywhere, from biomedical engineering. There are drug delivery systems, hyperthermia, 3D So we use electromagnetics in lots of fields. So if there is an application of electromagnetics, there is also a need for modeling and estimation. So this is why we need computational electromagnetics. And which fields are contributing to computational electromagnetics? First of all, we are trying to solve some mathematical equations. So mathematics is one of them. So normal formulations, robust methods, fast algorithms, error control algorithms, they are coming from mathematics. Also, we need to understand the physics. Not every mathematical solution means it is physical. So for design and other applications, we need to understand how physics work. Of course, we are writing code, we are coding and using computational resources coming from computer science and engineering. Also, there are different parallelization methods, special design architectures like GPUs and other platforms are coming from computer science. And we are engineers, so the important thing is applications. The problems for computational electromagnetics are coming from the engineering side, application side. So I want to briefly go over the methods in CEM. We can divide it into two branches. First of all, the analytical and sub-nanometer methods. The methods can be, the number of the methods can be increased, but we are lucky in Gebze Technical University. We have all of these methods, professors working on these methods. Professor Electromagnetic is working on evolutionary approach. There is Professor Ülkü working on dielectric technique, and Yuri Tushkin, Professor Tushkin, and Dickman is working on materialization. If we zoom into the numerical methods, actually this is not completely true. We can divide the first two branches in numerical methods. These methods are called full-wave solvers, and these methods are called asymptotic solvers. Asymptotic solvers, they are also called high-frequency methods. If the scattering mechanisms are modeled separately. For example, if you are using physical optics method, the transmitted and reflected waves are modeled, but refracted waves should be calculated separately with physical theoretic diffraction and added to the solution. Also, if there is a surface wave, this should be calculated separately and added to the solution. And there is also geometric optics, geometric theoretic diffraction, and there is shooting and bouncing ray method that can handle the multiple reflections at high frequencies. For the full wave solvers, there is no need to calculate the scattering mechanisms separately. All the scattering mechanisms are embedded in the solution. This is why we call these full wave solvers. So we can divide into differential equation-based and integral equation-based solvers methods. And all of them are divided into two, time domain and frequency domain. And we can name the famous ones: finite difference time domain, finite element method, discontinuous polarity method, gained popularity in the last 5 years, I guess. Also, in integral equation-based method, we have method of moments, and its accelerated version, multi-level phase multiple algorithm. And its method of moments time domain version is marching on time method. And today we will see marching on time method. If you compare the frequency domain and time domain methods, I'm not going to go over all these information, but what important one is the frequency domain and time harmonic domain, it is for single frequency. So for multiple frequencies or broadband data, we need multiple runs for the frequency domain case. Or we need to change the algorithm to wideband cases. On the other hand, in the time domain case, it provides the broadband data with a single simulation. Also, we can handle nonlinearities easier than the frequency domain. But we have a problem with instabilities, and it requires high computational cost compared to frequency domain case. I am not going to explain, I want to skip these slides because I will repeat them in the second part. And this is the end of the first one. Now we can enter the quantum theoretic model, how we develop it, and what we do in the Plasmonic applications. So here, our outline of the second slide, I want to talk about why we need for the quantum tunneling effect, why we need to include the quantum tunneling effect. And we developed a solution procedure for the include the quantum tunneling effect to the Maxwell equation solutions. I will explain all of these, then I will show some numerical results and complete my method. So, plasmonic devices gain lots of popularity due to the advances on nanofabrication techniques. So, there are lots of applications in the literature, like sensor design, biomedical applications, and etc. So, for the time domain analysis, classical electromagnetic solvers are used to model or analyze these structures. Usually, finite difference time domain and time domain finite element methods are used. But these methods are differential equation based, and they have some disadvantages. First of all, they need volumetric discretization of the whole computational domain, not just the scatter, but the whole domain. If you have an open field problem, then you need to end the computational domain with observing boundary conditions. And in addition, the time step size is limited by the Courant condition, which says the ratio of the mesh size to the time step size should be less than speed of light, speed of propagation. So I will come back to this slide, but I want to emphasize why these are important. In plasmonic applications, we got benefit of field enhancement close to the plasmonic device, or surface plasmon resonances close to the plasmonic devices. Therefore, the fields sometimes change exponentially fast. So to capture this, the field change, fine volumetric discretization is required. So due to this fine volumetric discretization, also time step sizes should be chosen very small. That makes the volumetric differential-based methods inadequate. On the other hand, if you use time domain surface integral equation solvers, we only discretize the surface, not the whole computational domain. And also it implicitly satisfies the radiation boundary condition. There is no need for an absorbing boundary condition. Most importantly, time step size does not depend on the mesh size. It is independent. But of course, always there is a trade-off. If you use the time domain surface integral equation, we have to use green function. And in time domain, green function means we have to calculate temporal convolution with green function. This is the problem that I will show how to do it. Second problem, why we need the quantum tunneling effect. Classical electromagnetic solvers assumes that the materials or structures scattered as rigid boundaries. It is very well defined. But in fact, if you go to the nanoscale, there is no rigid boundaries, there are energy bands. And some electrons can jump from one energy level to higher one and turn back, these things can happen. If you locate two nanostructures very close, less than 0.5 nanometer, sub-nanometer gap, then you will see that some electrons can jump from one scatter to other one and vice versa. Then there is a current, and this current should be added to the solution. Classical electromagnetic solvers cannot model this tunneling. So one can use the Schrödinger equation like quantum solvers, but quantum solvers usually very expensive. They need high computational resources. Even most of the problems, like if you don't want to analyze these two systems, even 20 nanometer, it's a very huge problem and it cannot be solved. It is impossible to solve with a quantum solver. So, if you can see, there are researchers from EPFR, Esteban, and co-authors, they suggest to use a fictitious auxiliary tunnel located in the gap, or located between these two structures. The gap is changed by the auxiliary tunnel. They solve the problem in the frequency domain, using frequency domain surface interpretation, and they determine the electrical properties of this tunnel by one-dimensional solution of one-dimensional Schrödinger equation. And how they do this calculation, first they take one electron problem for a given distance, and they determine the tunneling probability function. Then they use this tunneling probability in the static conductance. Then they embed this value inside the root model. We follow a different approach. First of all, we want to develop a time domain surface integration solver. So we need the transient analysis. So we need the time domain response of the conductivity, permittivity. And also we use the density functional pair computations to determine the electrical properties of the tunnel instead of one-dimensional Schrödinger equation solution. I will show what the benefits of these. So we developed a procedure shown here. First we have the geometry. We analyze the geometry and find is there any sub-nanometer gaps. Then, once we determine this sub-nanometer gap, we determine the tunnel model. In the tunnel model, we look at the maximum and minimum distances of the gap. Also, this figure is not up to scale. Actually, this part is very small, but to show it, we make it larger. Then, if the length is changing too much, we put some layers, not just a tunnel, but layers of tunnels. And all of the permittivity or electrical properties of the layers are different. And they are determined by the DFT calculations. So now we know the material type, for example, doped, and we know the gap distance. So we need to find the permittivity of these materials. In the density functional theory, we use VM2K commercial software, and actually we got the help of Udo Schwingenschläger's group in physical science and engineering at Karlsruhe. Recently, our paper published in Optics Express journal. The DFT has some advantages instead of one-dimensional Schrödinger equation for an electron. First of all, it solves many body problems, not just one electron. And also it includes the interband and intraband contributions to the solution. If we use root model, we will only have the intraband contributions. Okay. So what is intraband and interband contributions? We can see the energy level, energy band. Here, intraband with root model, there is only this movement of electron is included. The contribution is calculated. But there will be some electron movements from the energy levels, so we need to take into account these effects. I'm going to skip some of these, but we calculate the interband and intraband contribution separately, and these parameters are coming from the DFT calculations. For the calculation, we use a supercell, and this supercell is used to determine the permittivity of the bulk material, the spit, for example. And then we put a gap into the supercell and determine the permittivity of the gap alone for different gap lengths. Now we know the bulk material, the permittivity of the bulk material and tunnel. Now we need the time domain version of the time domain response of this. To determine the time domain responses, we use fast relaxed vector fitting algorithm. This is actually relational fit, and this algorithm is available in the web. It's open source. It assumes that the fit assumes that the structure of the fit is like this: Cm called the residues and Am called the poles of the fit. And if we must obtain the rational function fit, then we can obtain the time domain response by inversely Fourier transforming this function. And it is consists of exponential functions. But this is not enough. Finding the time domain response for permittivity is not enough. We also need the green function, because the green function in frequency domain depends on the permittivity. It's a function of permittivity. So we normalize the phase of the green function and extract the similarity and apply the vector fitting algorithm to this expression. Then we can again find the time domain response by inverse Fourier transforming this expression. Okay. So I will spend more time here in time domain surface integration part. Now we have the time domain permittivity, we have green function, time domain green function. Now we can build up our time domain surface integration system. To explain this, okay, we have layered medium. Also, there are some junctions here, but to explain the time domain surface integral equation formulation, let's assume we have only two regions, and we got the benefit of surface equivalence principle. So, in this first surface equivalence principle, first we divide the problem into two, and for the first problem, we place some electrical and magnetic currents on the surface of the scatterer such that it creates zero field inside and the same field with the original problem outside. Now, once we have zero field inside, the material properties inside does not matter. So we can change this to epsilon and mu1 with the background medium. So then, now we can use the green function actually. Otherwise, we can have the green function of the space defined by epsilon 1 and mu1. For the second problem, we do the similar thing, but we place some currents, J and M, that creates zero field outside, but the same field with the original problem inside. Then we can change the electrical properties and use the green function of the medium defined by epsilon 2 and mu2. So this is boundary condition for the equivalent problem, and boundary condition for the equivalent problem 2. You can see that this is the field outside and zero field. For the first problem, the fields inside are zero. And if we combine the first equation, this equation, and the third equation, and the second and fourth equations, with a combination factor, then we can have well-known different formulations. Like if we choose alpha and beta like this, we will have Miller formulation. And if we specifically choose alpha and beta -1, so we have Baggio, Miller, Chan, Bergman, Wu, Psi formulation. We use the boundary conditions, we use the surface equivalence principle, and this is our equation needs to be solved. And the scattered fields, the E1, E2, H1, H2 are given like this. So for the first medium, we assume that the background medium does not have dispersion. That means the epsilon and mu, permittivity and permeability are constant. So in time domain, the green function for such medium is given by the Gebze function, and this tabular convolution can be calculated analytically here. On the other hand, for the second medium, we have dispersive medium. So you can see the green function is not just a Gebze function, but it has a tail. So we have to calculate these convolutions every time for the matrix analysis. But there is another problem. We have convolution with green function, but also the permittivity is a time-dependent function. So it depends on time. So it appears in the time domain expressions as double convolution. So we have to calculate the unknown with the permittivity function and also the green function. Okay? This is all, now we come to the discretization part. This is well known, I guess. You already know the method of moments, I'm assuming a little bit. So in the method of moments, or in Marshall unit time, we expand the current density with some basis functions. Since we have two variables, time and space, we have two basis functions, spatial basis functions, fm, and temporal basis functions, t. For the spatial basis function, we use RWG routing and basis functions. And for the time to basis function, we use piecewise defined Lagrange interpolation functions. And here J and M are unknowns. If we substitute this expression in the equation here and do Galerkin testing in space and point testing in time, that means Galerkin testing is using the same function to test the equation, and point testing is actually sampling the equation in time. Then we can have an equation system. And now we can reduce the equation system to a multi-matrix system. This is a well-known multi-matrix system. You can see I is the current time step. Also, I should mention that if we don't have time here, you will see this is just a matter of moments. If you don't have the time dependence, if it is a frequency dependent, and you don't have the frequency dependency, this is just a matter of moments. So it is the time domain version. MOT is the time domain version of moments. But there is a difference here. The I is the current time step. We are observing the fields at the current time step I, and we have a summation here. Due to causality, this J is starting from 1, not 0, because there shouldn't be any field interactions before the time starts. And if we move the I time step on the summation to the left and keep the rest of the equation on the right, this is the equation we want to solve. If we use method of moments, then we have to put all these matrices to a big matrix and these unknowns to a big array and solve this. But here we are solving only the I time step. For example, for I equal to 1, there won't be any past interactions. These terms are related to the past interactions. We have the incident field effect, we know that. And we have the first time step unknown, and we solve Z0 to determine I1. Once we know I1, then we can use it to calculate the past interactions for I equal to 2, and we will have the tested incident fields for I equal to 2, and now we can solve this to I equal to I2. And it goes on I3, I4, I5. This is why this method called marching only time. Okay? And usually this Z0 matrix is sparse. Since you are not very low frequency, at very low frequency, this Z0 matrix is sparse and it is easy to solve with an iterative solver. Okay. Now I'm going faster than I planned. So now we have some numerical results. I have some numerical results. In numerical results, we use a plane wave with a modulated Gaussian signature defined by F0 center frequency and F dot F bandwidth. This is effective bandwidth. Before showing the numerical results, first we examine our rational function fit. And we use the Johnson-Christie model as experimental data, probably most of you know already. It is given for certain frequencies, but in time domain, we need the time domain version of it. So we use fast-fast vector fit algorithm, and there is also, in the literature, there is a 4-term Lorentz model. They use 4 Lorentz model and optimize the parameters to get the best fit for the Johnson-Christie. So you can see for the real part, the results are actually agreeing very well. But if you look at the imaginary part, 4-term Lorentz model is not agreeing very well. Our model has oscillations, but still gives a better model for Johnson-Christie data. And now we can use our function fit in the model, permittivity model, in the calculation of the time domain surface integral equations. Here we have a 50 nanometer sphere, and we excite it with a 900 terahertz center frequency and 600 terahertz effective bandwidth. And this is one of the coefficients of the solution. The blue one is the electric current density, red one is the magnetic current density. And if you look at the extinction efficiency, Like physicists usually look at the extinction efficiency, not the radar cross-section, but it is similar by definition. So we can see that time domain solution we obtain by time domain surface integral equation and frequency surface integral equation are agreeing very well with the near series solution. For the near series and frequency domain solutions, we directly use the Johnson-Christie model, not like it. Okay? And there's another information here. So we use equilibrium-based sampling of frequency band, and for it with 150 points. So we run 150 times the frequency solver. Then we can get 900. The solution we obtain for 905 seconds. But if we use time domain surface integral equation, we do it for only one time. We run for only one time, and the solution we can obtain at 335 seconds. You can see this actually, the samples are not equally spaced, but this is wavelength, so this is 1 over C over F, so it looks like they are not equally spaced. So for the second example, we have gold shell with the Johnson-Christie model. The shell is gold, and in the inner part we have silica core, and the radiuses are given like this 40 nanometer, 50 nanometer, and this is again one of the solution. And if you look at if you compare it to the near series solution, again our time domain surface integral equation solution is agreeing very well. Also, we apply this to some other examples that we can find in the literature. So there is a null field method given with this reference, and they usually solve rounded structures because in plasmonics they need to do some chemical process, and there is no sharp edges. So this is why they use rounded structures to model these kind of problems. And you can see our time domain surface integral equation solution is very well with the null field method. Now we come to the quantum part. So we have talk about DFT computations. Now we want to examine how DFT computations are they accurate or not. So you can see that with the Johnson-Christie model, if you compare the DFT calculations, the real part is actually pretty good, not bad, instead of better than the root model. But when we look at the imaginary part, for the high energy values, our DFT is closer to the DFT solution is closer to the Johnson-Christie, but for the lower energy values it is not. Root model is better. And we use these permittivity models to get the solution and to compare how the effects are. And we see the same effect with the permittivity. Like if you look at the DFT computations, they are agreeing actually very well, better than the permittivity with the Johnson-Christie model. But after a while, it gets worse, and the root model becomes better. Okay, now we have the tunnel model. Here we have two spheres called gold diamond, and we want to use the DFT model. The gap distance between these two models are 0.1 millimeter, and the radius is 25 millimeter. So this is one of the solutions, and our excitation has 785 terahertz center frequency and 665 terahertz effective bandwidth. The first thing we test is our layers are accurate. How many layers we need? So if we increase the layers from 1 to 4, you can see that the solution is converging to the fourth one. Even if we do more, they are on top of each other with 4 layers. So it looks like 4 layers is enough to model the tunnel. And the second example, we changed for the second application, we changed the gap. We want to see the effect of gap from 0.1 nanometer to 0.5 nanometer. Here is a resonance frequency that occurs in 1.8 electron volts to 1.5 electron volts, and it is getting redshifted. And there is another one appears if the sphere becomes closer. This is without the tunnel. There is no tunnel case. If we add the tunnel, quantum correction, the graphs are totally different. So there are two resonance frequencies, but they are separate from each other. One of them is almost 1.2 electron volt, and it is getting blue shifted. And there is another one almost in 2, and it is also getting blue shifted. Okay, obviously we need to take into account the effect of the tunnel movement. And we do the same thing for the silver diamond. For the 506 terahertz to 506 terahertz center frequency to 493 terahertz bandwidth. And you can see the oscillations on the solution, so there should be some resonance frequencies. And this is without the tunnel. If you look at the solution without the tunnel, you will see two resonance frequencies. They are close to each other at 2.6 to 2.8 electron volts. And one of them is getting redshifted, the other one is getting blue shifted. If you look at the quantum corrected version, then you will have two resonance frequencies, but they are separate. And one of them is at 2.6, and the other one is almost 2.3 electron volts. So obviously, the quantum correction is required. And I'm really fast. So this is the conclusion and of my talk. We propose a new quantum corrected model. We determine the permittivity of the tunnel, the quantum correction with the density functional theory computations. And we can now do some time domain simulations with time domain surface integral equations. To do it, we developed a time domain surface integral equation solver that can handle dispersive and dispersive media, where the permittivity or permeability depends on the time. And what are the important parts are we developed, we can handle double temporal convolution that appears in the dispersive media and closed media. Then we can use any kind of permittivity model. It doesn't matter if it's experimental or if it's closed form. And also, we can determine time domain wave function from these models. And most importantly, we can do quantum correction by dielectric computations. What is next? What we need to do in the future? First of all, these solutions are not accelerators. These are direct applications of much volume time. And we don't accelerate our solver with FFT-based accelerations. Another application is we can model, this is for sub-nanometer gaps, but we want to include the semiconductors and electron hole interactions to our calculations. So it will widen our application area. And another application area is we can couple the equations. Instead of putting a quantum corrected model, we can do a domain decomposition, and we can solve the inner part, the quantum part, with a Schrödinger equation solver like DFT, and we can solve the rest with the classical solver. And actually, now we are working on the electron energy spectroscopy, because so far we don't have any experimental data. This is just an estimation. So we want to validate our results with the experimental data. And luckily we in KAUST, in King Abdullah University of Science and Technology, we have an EELS facility. So these days we are working on EELS simulations. Okay, thank you very much.